Beautiful.
So, I would like to congratulate the following people: Amma, Ariana, Nina, Carly, Megan, and Kitra. Megan, really? Where's Megan? Good job, almost done. Kitra, done. Oh my God. Thank you. Good work. So that's 1, 2, 3, 4, 5, 6. That is 6. We have 18 people in our class. Get on that, right? So web work, make sure, at a minimum, make sure you can freaking log in. Right? We got a big, long holiday coming up after Friday. So here's your new assignment. Again, by Friday, have logged into web work. Okay? If you have not, log into web work. Because like once the weekend comes and then you're like trying to get this done, it's the weekend. I may or may not check my emails a lot on the weekend. I can definitely tell you on Saturdays I don't check my emails. That's my day off of email. So that is your job. Let's see. So we are good on questions. We got Nina's questions. No other questions on the web work? Oh, yes,
I have a question about world class.
Yes.
You said you wanted us to take the pre-assessment,
Yes.
but all that's listed is a post-assessment.
Well, that sucks. I better fix that. I will fix that.
Okay.
You didn't do it, did you?
No.
Okay, cool. Nobody started the post-assessment? Okay. CCI fix. Thank you. I will fix that. So if you're new to the class, or first day here, some people have been here, it's their first day, you have a bunch of things to do. You need to log into web work and ensure that that is something you can do. The details are on World Class in an announcement. You also need to take the calculus concepts inventory. And that has to happen by next Friday. And remember, don't guess, because it doesn't matter what your grade is. In fact, not guessing is preferable so that you can improve. If you're just guessing, you might get it right. That doesn't show us anything. So, don't know, leave it blank, move on. Take you an hour tops. Time for no shoes. All right, friends, let's take our moment of silence together. So just sitting up, closing our eyes. I'm going to take my glasses off for a second. And if you can, maybe pull away from the back of your chair so that you are supporting you. It's just your own strength holding you up. That makes it a little easier to not space out. Just relaxing our face, checking the tension in our jaw, seeing if we can let go of a little of that. Letting our shoulders fall down and back. Starting to notice the sounds in the room. Find yourself thinking about what will happen or what has happened. That's natural and okay. Gently bring yourself back to being a scientist about the sound in the room. Be incredibly curious. Now notice what you see with your eyes closed. that space. So shimmering, maybe there. It's not just completely dark. With a wide gaze and a soft, relaxed eye. What do you notice in the space of your mind, the sky of your mind? Can you incorporate both these sounds in your visual field at the same time, noticing both? And let's just gently come back. Oops. Open our eyes. Go around. Hi, everybody. All right, let's do some calculus. Okay, so let's see. Where did we leave off? We left off talking about average velocity. And let's refresh our setup for those who were here and those who just joined us. Just how is this all rolled? So S of t is a function that describes the location of a point on a line. So this is equal to the position of a particle on a line. So again, we've got a line. So think of this as a string, a very taut string or a wire, and we have a bead that floats on this wire back and forth. And we need some kind of reference. We need to know where home is, so we'll pick zeros here. And then I've got this little particle, and this distance is S of t. If S of t is negative, I'm on the left. So here we have S of t positive. If I was over here, this would be S of t is negative on this side, over here. And so it's just simply the position of that particle. We define the average velocity of this particle over a time period. So we said AV, and we're using our book's notation. Average velocity over this time interval is equal to our position at the end minus our position at the beginning over the change in time. And then we also talked about a little bit of notation. This is the change in position over the change in time. Just using that delta notation, that delta representing change in a quantity. And then we got off on a tangent, right? Because I wanted to talk about sine and cosine, and then we started talking about sine and cosine graphs. So let's see how much of that you remember. Can you quickly sketch the positional behavior if this is the function denoting, without like a reference, just what do you remember? It doesn't matter, you get it wrong, who cares? We'll figure it out. What is a sine, the trick, what does a sine graph look like? Do you remember that? Can you do that from memory? And I think like next Wednesday we should have a quiz on this. Closed note quiz where I say sketch sine, sketch cosine. So I would practice these things by next Wednesday. So you have them. You own this. You've become mighty. It's slightly more powerful mathematically. And I'm putting it up here if you don't want to see. Just sketching the periods for it. One period, just a single period of this thing. So remember how, just a quick refresher, I draw this box. The box is 1 unit high, 1 unit deep. So 2 units high, I guess, essentially. 0 to 2 pi is the natural period. I cut that in half, that's pi. I cut that in half, that's half a pi. And so now I've established what my units are here. This distance is half a pi. So between here and here, here's 1 pi, 2 pi, what's in the middle? 1.5 pi's, right in the middle. Sine starts at 0, goes to 1, goes to 0, goes to -1, goes to 0. Let's do cosine really quick, so we have these out. S of t is cosine of t. So let me step through this while I'm drawing it. Cosine, a lot like sine, just has a different rhythm. It's going to be 1 unit high, 1 unit low. Make a little box. Wherever you make this right end of this box, that's going to be 2 pi. That's 2 pi, so halfway must be pi. Half that must be pi halves. And in the middle here is 3/2 pi. Does this sound good so far? Yeah? So now, the dots are going to be different. Cosine starts at the highest spot. So here's, cosine starts at 1. Cosine of 0 is 1. Goes through pi over 2, comes down to -1 at pi, comes back up, and back up. Let me ask you something. Don't draw this. Is that what cosine looks like? No, ouch, right? That's like a razor. That's sharp. That's what you saw logs with. That's not what you make music with. We want a beautiful sinusoidal curve. So don't make your sines and cosines sharp. Make them luxurious and lovely. Well, okay. Could be lovely. This goes right through that. And then if I want to repeat this, I can just cookie cutter these things. Before we go on, let's see if we can apply this information. Yes, yes. Sir.
Wouldn't, if it was tangent, wouldn't it just be the same because the tangent of the triangle on the unit circle is always going to be like 1 with a radius? Or would it be graphed differently?
So tangent's a whole different beast. Tangent, so if we were to look at tangent of t, I like this question. So it's the ratio of sine to cosine. So essentially what I'm doing is I'm taking the height here and dividing it by the height here. But when I sketch out a tangent, notice that in that case I would be dividing by 0 here. So at pi over 2, I've got a horizontal asymptote. If you think about extending this, at minus pi over 2, I'd also be dividing by 0. So I have another asymptote there. And then the tangent actually is asymptotic at those points. It looks a lot like that. And then that cookie cutters back and forth. So let me explain that to you in terms of the unit circle, which is where it sounds like that's where you're coming from. Let's go to the unit circle. And tangent, thanks for taking me. This is like one of my favorite stories, so I appreciate you asking. This rhyme, we know, for trig functions and stuff, is definitely helpful. Some idiot teacher screwed this up for all mathematicians last semester. Did y'all see the kerfuffle with the jackass lady who was singing this like as though she were an indigenous person? And wow. Anyway, I'm going to use it because it's a great mnemonic device. Just say SOHCAHTOA. You don't have to say it in any specific way. But what this means is sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. And tangent equals opposite over adjacent. Now, what? Adjacent what? Hypotenuse what? Well, this is all in reference to a triangle. So if I have a triangle, like so, and I have an angle theta here, then this side is the adjacent side, this is the hypotenuse, and this is the opposite side. These whole first weeks, this is the kind of shit we're gonna be doing. I want you to be like so powerful at mathematics and to refresh your memory and all these things and become stronger at them. Trig is where generally everybody is kind of like, yeah, I can do it, but it's a little rough. So when I look at this, and I say to you, what is the tangent of this angle? It's this length over this length. In fact, let's get a couple triangles that you should have. I would put these, I would start making a little note sheet, or if you already have these things in your head, that's great, but you want to be prepared. Start preparing for the first exam now. Make a little note sheet, and when you write these things down, it strengthens the correspondence in your mind, strengthens the idea seed or whatever. There's two triangles that you absolutely should know. If this is 30 degrees, and this is 60 degrees, that's a right angle. This is a 30-60 triangle. This side is 1, square root of 3, and then how can I find this side? Yes, you're saying that? It's hard to tell. Okay, yes. A squared plus b squared equals c squared. Whose theorem is that?
Pythagorean.
Oh shit, yeah, yes, Pythagoras. Can you believe this? Like this Greek dude. Couple thousand years ago, Pythagoras. We're still summoning Pythagoras on a daily basis in our math classes. So what you will see occasionally is me bringing a brazier of coals to class, igniting it, throwing offerings onto the brazier, and summoning from Hades our good friend Pythagoras, who was frankly kind of a freak. The Pythagoreans were a weird bunch. I won't go into the details, but over the holiday, look up the Pythagorean cult. I'll spare you. But yes, I could use this a squared plus b squared equals c squared, referring to an arbitrary right triangle, like so. So this squared is 3, this squared is 1. And so that must be this side squared. So this must be 2. Good news is, all I have to do is remember two of these things and I got the others. So that's a great triangle to have ready. Now watch what I can do. Now you might be like one of these, who are our unit circle fiends out there? Yeah, so you memorized the unit circle maybe or something like that, right? Is that right? Yeah. A lot of people have that. Or you have a little unit circle on a clear piece of plastic that you could look at, right? One of those sheets. So I like this better. Because if I know SOHCAHTOA, I know this triangle, and I know this triangle, the other most awesome triangle. 1, 1. Thanks, Pythagoras. I know a lot of trig values without a calculator because I know these and I know SOHCAHTOA. So if someone said to me, what is the sine of 30 degrees? I would look at my triangle, I would look at 30, I would think opposite over hypotenuse, so this is going to be 1/2 opposite over hypotenuse. What is the tangent of 45 degrees? Go to this triangle. It's opposite over adjacent, so it's 1/1. 1. Now I own a bunch of trig values, exactly, and I will want you to own them and use them precisely. So, still haven't gotten to your question yet. Your question was, what's going on with this graph over here? So let's take a look at that. we talked about the unit circle last class, and if this is t right here, then the tangent of this angle is going to be this height, the opposite, over this height, the adjacent. And let's think about how that rolls. How does that change, that ratio, as this angle moves? So like, where do we start? Well, start here at 0. What kind of sad-ass triangle is that? That is a degenerate triangle. And I'm not being derogatory. That is a degenerate triangle. That's the legit term. Because it's a triangle that looks like this. 1, 1, 0. Has no height. So the opposite side has height 0. The adjacent side has height 1. So the tangent of 0 is 0. Now what happens to that ratio as we move up? Watch, let's just think about it. So like right there at 45 degrees, pi over 4 radians, the opposite and adjacent have the same ratio, so that's a 1. So right here at 45 degrees, that must be 1. And then what happens? Let's look at a triangle that's really close up here, so like this guy right here. Woo. So now we're kind of approaching this degenerate triangle in a different light. What is the opposite side getting closer to? What is, 1. Yeah, and what is the adjacent side getting closer to? 0. So we've got 1 divided by a really small thing. That's a really big thing. So what I see is that as I approach up here, the tangent becomes larger and larger. And then right here, it's not even defined because there's no opposite side, or the opposite side is 0. Or excuse me, adjacent side is 0. Does that make sense? Okay. It'll sit inside there. Any other questions to clarify anything that I've said so far? And I do know it's Olivia. I thought about that a lot. You will never be called Alina. Although that is a nice name. There's nothing wrong with Alina. It's just not your name. All right. So, back to the problem at hand. Sketch sine and cosine. And then let's find some things here. What is so working with this function, find the average velocity on 0 to 3 pi over 2. So now what is that going to be? It's going to be s at 3 pi over 2 minus s at 0 over 3 pi over 2 minus 0. What is that? Don't need a calculator, right? Because we can look to the right. Everybody a chance, make sure we're all on the same page. What did you get for this one? Oh, okay, cool. Okay, I saw you right. This one thought maybe you had. Who's got this? Feels good about it. I will start calling on people. I just did. Oh, poor Amma had to pay. Somebody else must pay.
Nobody's raising their hand.
Who is that? Oh, yes. Megan?
No, That's.
Callie.
Yeah.
Callie, hi, cool.
I got -1/3π/2.
Yeah, I like that. That's beautiful. How did you come up with these values?
I just did the sine of 3π/2, which is -1, and then the sine of 0 is 0. So that's how you get the top, and then 3π/2 minus 0 is just 3π/2.
Perfection. Beautiful. All right, so to find these exact values, so let's actually convert it in, let's plug that into the function. It's going to be sine of 3π/2 minus sine of 0 over twice π/2. And then I want to know what these values are, but I do. I own all sorts of things about sine because I can look at that picture and I can see that the sine of 3π/2 is -1. And I can see that the sine of 0, just like Callie, was 0. And then we just got this down here. And there is nothing wrong with that. It kind of doesn't feel aesthetically beautiful to me. So what I'm going to do is, this is the reciprocal of 3π/2. So I'm going to make it 2 over 3π. That just seems pretty. This is right. That's pretty. Less fractions. If you got a bunch of fractions within fractions, that's not appealing. You like to simplify fractions. Same value. All good. Beautiful. Let's do some more. Let's leave these pictures up. What is the average velocity? Oh God, before we even go here, what is this particle doing? What is the movie associated with this particle? This particle. What is it doing? Yes, yes.
Is it swinging back and forth?
Is that, are you clear?
Yes.
Yes, clue. It is. So it's, yeah, it's just moving back and forth on the wire. It starts off right in the center of the wire at 0. And remember how to think of this. Each one of these is a slice of the movie. You can literally look at what the wire looks like by just grabbing a slice at that time. So we see here that here's the first scene. At time 0, we're at 0. At time π/2, we're at 1. And we move that way, right? So it went like this. It went, it hits 1, and then it starts coming back. So it's kind of got this behavior like that. And then it goes back through 0 again at t = π. We're back at the origin. And then we move to the negative side, up here. And then we move all the way up at t = 3π/2 to a -1. And then again, this is going to happen. So it's just bouncing back and forth forever and ever and ever. It's harmonic motion. Well, however you spell motion. So, let me push some more challenging things up here. What is our average velocity from 3π? Sorry, I got to figure. Now I'm trying to do fractions in my head. And to 11/2 pi. You're going to need to figure out what the graph looks like out there. So you can take your picture and extend it out. And if you're like 11/2 pi, just realize that's just 5.5 pi's. That might help. Let's extrapolate. Put a new one of these for us. Olivia, you think you got, feeling good about it?
Maybe.
Maybe, cool. Can we chat?
Sure.
Thank you, wonderful. Yes, ma'am, so, what are you thinking here?
I'm thinking it's -1.
Cool, can you walk me through your thought process?
So that would be s times 5.5 pi minus s of 3 pi.
Yep, I love that, all over.
Divided by 11 pi over 2 minus 3 pi.
That's beautiful, what a great setup. I love it. So, let me translate, then that's gonna be sine of that, right? And at the bottom, did you simplify the bottom?
Yeah.
What'd you get?
I got 2.5 pi. which
Yeah,
is-
beautiful, beautiful, so 5 pi over 2 down there, yeah, same thing, exactly. Okay, so what was the sine of 11 pi over 2?
I got -1.
Beautiful, and I think we agree. Does everybody see? We got here, Olivia and I, we're on the same plane. We extrapolated this picture all the way out, and we got -1 out here. You don't have to draw the picture if you're good at catching rhythms. Totally, do what you need to do. But I wanted to make sure it was exposed for everybody up here, so love it, -1. So then this is gonna equal -1. And then Olivia, what was that sine of thrice pi?
0.
Yes, ma'am. Fantastic. So we got that. Over that. And that's a hunky-dory answer. And that's what you had, right?
Yes.
Kind of. It wasn't what you said exactly, was it?
No, but it's close enough.
It's hella close. I think you just left off that denominator when you told me the answer.
Yes.
Beautiful answer. Any questions on this answer? How could I make it prettier? Now I actually even have a sense of what that value is, because pi is like 3. So this is like 2/15, right? And I have an understanding of the magnitude of this quantity as well, just intuitively, no calculator needed. Okay. Good. Let's move on. Let's try some other stuff. I think we'll hit trig every day. Here's a new one. Here's a new thing. New position function. What is that? Can someone tell us what that is? What did I just write on the board? I mean, I know.
Isn't natural log LMS log?
So it's absolutely related to natural log. It's not natural log, but it sure the hell is close to natural log. It's the companion. Who's this? Yeah.
It's E, which is the natural base. E is the natural base.
Oh my God. Don't try to woo me with all this fancy talk. This is beautiful. This is the base of the natural log. Yeah, absolutely. So this number E here, let's talk about E. Absolutely exists because of calculus. This number is because of calculus. It is one of the 5 most important numbers in all of the world. What are the 5 most important numbers in the world? There is 0. Without nothing, you can't have something. Absolutely fundamental. Without something, you don't have anything. So here's nothing, here's something. Here's a great one. We've already seen that today. Next one. Yeah? Our buddy that I'm about to tell you about. And then one more number. We're not going to ever touch on it in this class. Yes, yes. Hi. Yes! Do you know what I'm thinking of?
It's an imaginary one.
It is. So I is the square root of -1. Do you know the equation, Euler's equation that links these all up? Does anybody know that? I see Claire racking her brain. Does anybody know the equation I'm thinking of? There's one equation that links all 5 of these numbers together. I'll tell you. This is called Euler's equation. Euler is as close to a demigod in mathematics and science as we will ever know. Truly, just one of the most prolific scientists, mathematicians ever. Hands everywhere. Euler's equation says e to the I pi plus 1 equals 0. We don't have time to understand that strangeness. But that is a truth of the universe. That is a deep truth of the universe. So true that I've known at least 3 math majors who have this tattooed on some part of their body. When you go to Calc 2, and I hope you do, this fall with me. I hope I see some of you in Calc 2 this fall. I will prove this to you. I will literally prove that to you. But for right now, we'll just say, what a beautiful sight. It's like wingsuit jumping. Like, I love watching people wingsuit, but there's no way in hell I'm ever wingsuiting. And I don't even know how to begin. This is mathematical wingsuits right here. I'll do it in Far Cry or something like that, but that's about it. So, E is Euler's number. Oh, how convenient. You know that when you've got a number that's named after you, you have done some shit. Right? So Euler's number, and it's approximately, it's an irrational number, which means it can't be written as a fraction. And it's like 2.7, 18, 28, 182, 8. What you should just keep in mind is Euler's number's like a little under 3. If you just know it's like roughly 2.7, you're doing better than, I would say, about 99% of humanity. You know more about E already. Here's some ways you could write E. You could write E like this. And let that sum go on and on and on. So this infinite sum would add up to E. It's a very pretty sum. Notice the beautiful rhythm under the denominators. There's lots of other ways to write E. I'll spare you for right now. Really all I want you to know is this. And I also want you to know what Nina said, that it is the base of the natural log. So when we write ln of something, this is the natural log of x. That's how I would read that. And what that means is it's log base e of x. And what that means is that this is the number you have to raise e to get x. That sounds weird, right? But what this is, logarithms are just exponents. They're the exponent you have to raise the base to get the thing you're taking the log of, which all sounds like I'm just spinning around in a circle. So this equals the power you need to raise e to get x. So that's what a natural log is all about. It's the inverse of e to the x. Okay. Know this graph. So know this. know this and know this, what I'm about to put up. Here's the graph of E. So if this is, whoo, that is a drunk axis. Asymptotic, the closer I move, the further I move left, the closer this gets to 0. It crosses the y-axis at 1. So in other words, e to the 0 is 1. And it blows up as we move out this way. So let's write a few things. As x tends toward infinity, e to the x does also. As x gets bigger, e to the x gets bigger. That's all I'm trying to say there. Being suggestive of some notation we'll get really good at. As, let's write this over here, as x becomes more negative, e to the x becomes closer to 0. So notice I'm taking that picture and I'm now adding some language and being more precise about that picture in ways that we will want to be precise. Okay. Let me give you a second to get caught up. I know I go like a freight train once I'm going. I don't quite know what it's like to experience it. I hope everybody's okay. We okay? Cool. Yeah, good, okay, good. People still capable of nodding, fantastic. We're still sentient. Out freaking standing. Okay, so if I gave you this function, what is the average velocity from 0 to 3? Simplify as much as possible. There's not very far you can go. Give it a shot. Adrian, do you think you got this one figured out? No. Okay, okay, fair enough. Victor, we got anything? No? Okay. Juan? Cool, I'll just keep cruising. Kelby? Working on it? Okay, fair enough. Megan?
Possibly.
I'll take it. What you, walk me through it.
Okay, I might have done this wrong, but I did E of 3. Or E of like, and then I did this wrong. Because I did like parentheses and I put the 3 in the parentheses, like if it was S.
Oh, I like that. Okay, so let's actually use the S notation. So like this.
Yeah,
right,
and
yeah.
then
Beautiful.
Minus S of 0
Yeah.
over 3 minus 0.
Beautiful. That's fantastic. So right here, if we had an exam, you just got a lot of credit. What's the next step then? What's S of 3, Megan? That's okay, and it might seem weird. You might not know what to say. Yes.
Would
Adrian.
you be, are we expected to solve this like exact?
Well, exact, but you don't need to know what the value is.
Yeah, that's what I meant. Would it just be e to the e cubed?
Yeah, perfect. Yes. Is that what you're?
Yeah, I was gonna say 2.7 cubed. but-
Woo! Yeah. Close to 2.7 cubed. This is as good as we can do.
Well, that's what I was asking.
Yeah, exactly. So let's leave it precise like that. That's beautiful. Then what? What's S of 0?
1.
One.
Beautiful. And then, yeah. That's it. That's as good as we can do without a calculator. This is beautiful. Because when you're communicating numbers to a person, you've just done some work for your boss, you just did this computation. This is what you give the person who's using it, because now they can get as much precision as they want. Right? This contains infinite amount of information. If I do this, and I don't ever want you to do this. I wouldn't want you to do something like this, because that's a freaking lie. That's a lie. That's close. But good Lord, if we're sending something into space, like that's not going to cut it for Elon Musk, right? We're trying to land something on a meteor somewhere, or a comet billions of miles away. We're going to give them this computation here. This misses things by a mile. So I understand the discomfort with it, not quite knowing what to give, but I like precision when we can do precision. All right, any questions on that, friends? All right, let's push forward a little bit. And let's get off of this stuff. At least the review kind of thing that I'm doing here. Let's chill out a little bit. Let's relax. You're gonna like this. Here's the gift of the day. Just an old square, just a quadratic thing. How beautiful is that? Could you sketch S of t for me on your own? And for negative time as well. If this is t and this is S of t, take a minute, try to get a graph of the behavior, then see if you can picture the movie for all time. Just so much want to get in this little box. There's like this little, I'm just gonna do it. Get in there. Okay, that felt pretty good. Little gnome house. Dude. Yes? The old parabola? Cool, good, good, good. You know if you got it, and if you don't, now you know. So what is the bead doing? What's the movie on the string? 0. Time, oh yeah,
Starts out way above there. Or starts way negative, and then it starts going positive, and as time increases, it starts slowing down, it's pretty fast.
Yeah, and I think you got the picture, but I think your language is being a little, so notice that the position is actually never negative, right? S of t is always positive, so, but when t is negative, we're way out there. So like when t is negative 1,000, we're way out here. As t moves closer, remember how this works. These are slices. This is a movie of, this is a stack of film slices. And each vertical slice shows you a picture of the strings. Here's the string actually keeps going. This is the right half of the string on top here. So you see the bead moving closer and closer to 0. So it comes in like this, slows down, touches 0, and then cruises back on out. I want you to be able to make these movies in your head and understand these pictures. So let me stop. Does that make sense? All right, cool. So let's find some average velocities. could you please, dear friends, find the average velocity from 1 to 1 plus h. And here I'm going to tell you h is a positive number. Just follow the formula. This is you might be like, what the fuck is this guy talking about? Just go with the formula. The average velocity formula, then simplify. What can you get out of this? Get this as simple as possible. Let's see if the dean emailed me back. I sent a nasty email this morning. We don't have any N95s in our classrooms. Dean has not replied. Make sure you're on the right track. First step, yeah? Everybody good on first step? Just plug it into that formula. I find that a lot of folks have trouble with functions in calculus. You've got to, if you're not quite sure what this means, or what happens after this looks weird to you, talk to me. You need to do some work in Alex. You've got to understand function. This class will just be a nightmare if you don't understand function notation. So let's go here. So what is S? S is just the rule t to square it. So here's what that function S is. Take whatever's inside here and square it. So in other words, when I've got 1 plus h in there, when the thing that's in here is 1 plus h, I literally square the whole thing. So this is just shorthand for this. S of 1 is just 1 squared. And then this down here, that turns into something real happy because the 1's cancel. Let me stop. Questions? True or false? Don't say it out loud because I don't want to know if it's the wrong answer. I'm not going to make eye contact. I can't. True or false? False. False. This don't happen across sums. You can't bring exponents across sums like that. So that is a lie. It's a foul thing. How do I have to get this figured out? Foil, yeah? Foil that sucker out, or do this. Or I'll show you something a little cooler come Friday. But you can work this through. Get that. The 1's cancel. And now, let's talk about how to simplify more. What I've seen a lot of is people just canceling these h's out like here and say, oh, that's 2 plus h squared. That's a lie. You can't cancel from a sum. When you have a fraction, you can only cancel from a product. So the first thing I would do is factor the top. Here I'm gonna factor. Now I can cancel, and I'm left with 2 plus h. That's the answer to this. Yes, sir.
With the canceling step, could you also just like divide by h? Because 2h divided by h is 2, and h squared divided by h is just h?
Yeah, absolutely. If you think of this as, you could break this apart like this. That's totally kosher too.
Okay.
Yes. Just realize that that's what you're doing.
Yeah.
Yeah. Beautiful. Other questions? Okay, so let's draw a picture. What is going on here? I'm gonna come back to this. Let me fix my picture up. We're about to do calculus. We're damn close. We haven't done calculus yet. We're just thinking calculus-y ways. So, okay. Here is my friend. Average velocity from 1 to 1 plus h. So let's say here's 1. This must be 1, because 1 squared is 1. And then if 1 plus h, I said it's a small number, so I'm not going to go too far. So this is 1 plus h quantity squared. I'll put 1 squared there to be suggestive. And then look at that average velocity computation. It's the change in height over the change in width. Notice that, change in output over change in input. This is calculus. Calculus is, the first half of calculus is all about studying the change in output with respect to the change in input. And that's what we're doing when we make that computation up there, that average velocity computation. So this distance right here is just that minus that. This one here is just literally freaking h. So, what have I found? When I'm finding the average velocity, I'm really just finding the slope of this line between these 2 points. So let's put that up here. So the AV, 1 to 1 plus h, equals the slope of the line between these 2 points. It's just the rise over the run. What is happening as h gets smaller and smaller? So now look at this. We've actually figured it out. We've done the whole thing. We know that this slope, we have a formula for it. It's this, 2 plus h. So no matter what h is, I've got the formula. Yes, sir?
Is that the slope of the average slope between those points, or the slope of the line between those points?
It is literally it is the average velocity on this time interval, but it is the exact slope of the line connecting these two, not the curve.
Not the curve. Okay.
Yeah, but the straight line. Is that what was kind of confusing? Yes. So if I draw a line between the endpoints, I make a nice little right triangle, and it's close to the curve, right? It's kind of like the curve, but not exact at all. The curve actually lives under that line, just a little bit. So, what happens as I start bringing these 2 points closer and closer together? Well, let's figure out, what is the slope? What is the average velocity from 1 to 1.1? What is h here? 0.1. Yeah, beautiful. So I can just go right to my formula. It's going to be, average velocity is 2.1. Let's get some units. Seconds, meters. So this would be 2.1 meters per second. what is the average velocity from 1 to 1.001? What's h here?
0.001.
0.001. So this is equal, what would be my average velocity? 2.001, right? Yeah, it's this 2 plus the little change here, meters per second. What is happening to this line here as these 2 points get closer and closer together? Let's think about it. Now, when the points are really far apart, I need to make this curve a little bit more exaggerated. There we go. So let's say here's 1, and then here's 1 plus 1. This is called a secant line. As it gets closer and closer, think of this as being attached to, oh shit, we gotta pull up a computer thing. This will be better. No, you go. Hopefully I'm not driving everyone out. Can't take it anymore. We've only got 10 minutes left. This will be it. I'm going to show you what happens here, and then we'll call it a day. But it's so much easier with a computer. All right, I got to wait for the rodents to wake up that power things here, whatever. But what we are doing is I want to think about what happens as these 2 points get closer and closer together. So think about what that line is going to look like. What happens when those 2 points coalesce together? The left endpoint and the right endpoint. What happens to that line that I'm drawing between them? And what you're going to see is that it actually becomes a line that touches at just 1 point. That is called a tangent line. So what we're doing is we're getting closer and closer to the tangent line. And the final answer, when I let h equal 0, when the distance between the top and the bottom are 0, what do we get for our slope? What happens when h is 0? Over here. Right here. 2. So what that's telling me is that the slope of the line that touches this curve right at 1 is actually exactly 2. Now, if you're like, what the hell is happening? And you might be. We're going to talk about this a lot. Yes, sir.
If h is 0, then wouldn't you have divided by 0?
Yes, up front. So you're right. At front, I can't actually do this computation until I do the simplification. So I can't let h be 0 until I'm no longer dividing by 0. But notice that all the math we did, that's an awesome observation. And in fact, we will never actually just let h be 0. We will let it approach 0. But notice that this computation is, like, when h is 0 here, this is bad, right? As you noted, I'm dividing by 0. But if I come through here, all of a sudden, things simple, so all of a sudden I'm not dividing. This quantity is exactly equal to this quantity up here when h is not equal to 0. This quantity doesn't exist when h equals 0, but this, you agree this one does, right? So these two quantities essentially act the same. So think about what's happening when h is very small. We're getting closer and closer to 2. Notice that the smaller h becomes, the closer this output becomes to 2. Right? You can see it right here. So what we're doing is actually taking a limit, and that's the thing we're going to start talking about for the next couple of weeks. So just this basic idea. But I love that you caught that. Up front, I definitely can't let h equal 0. But after some algebra, I can. And it's okay here. So let's take a look at my computer, buddy. Did that come on? kind of. Oh, boy, oh boy. I am really playing with fire here. Why do I keep doing it? There we go. Okay. Give me 1 second. Let me just kill the lights real quick. We've got like 6 minutes left. Ooh, that's relaxing. Soothing. Okay. So little computer demo here to show you what's happening in a way that I can on a board. Come on, Gophers. There we go. All right. So I'm going to use Desmos, and I'm going to look up some instantaneous velocity app. I think this is the one I want. Beautiful. Let's get our function in. So notice they have a position function, S of t. Somebody was doing calculus. There's t squared. Let's back out. Let's do this at 1. I want to adjust that. Boy, I hate the scale on that thing. I don't know how to change the vertical scale. It's quite intense. Okay, well, we'll do what we can here. So let's go back. Here's the H. Here we go. Okay, so notice how as I change H, that right endpoint changes. Let me back out so you can see it. Oh, this is great. This will work. So see, here's when H is 2. And those 2 points are really far away. And if you look right here where it says M, that is the slope of that line. So this M equals 4 that I'm seeing right here. I got my cursor over it. But that is the slope of the red line, the secant line between those 2 points. Watch what happens to the slope as we shrink H. So now you can see the line, right? Those 2 points are getting closer and closer together. Let's get in tighter. And notice, what is the slope going to? Check it out. Right now, H is 0.1. The slope is 2.1. We knew that. Let me adjust my precision here, my step size. So now I've got a little more granular control. And watch, look at that slope, 2.04. And now it's barfing. But look at what it's getting closer to. That's the thing. It's 2.01, and shit, can I get better? Oh, it won't even let me do a better step size. I wonder if I can do that. Oh, I can. Look. Oh, this is beautiful. I can just manually do this. So when H is 0.01, the slope is 2.01. When H is, look at this. Oh, man. This is great. Now, anybody know why the formula, any computer people in here know why when I add this next 0, like everything looks terrible? Any computer folks in here? It's because the computer is trying to do math that it's not, doesn't have the precision to handle. So it's rounding up and doing all sorts of things to give us a false answer. The key thing, all I want you to know is just for Friday, and I'll let you go, as these 2 points coalesce, we achieve a slope that represents the instantaneous velocity. Instantaneous velocity is what you read on your car. When you're cruising in your car and you're looking at the speedometer, that needle is constantly moving. It is telling you at any instant how fast you are traveling. It's not taking an average, it's your instantaneous velocity. And so that's what we're going to pick up with on Friday. We will meet on Zoom. I will send you the link. I'll have office hours tomorrow. I'll send you the link. Thanks for being here, everybody. Yes, sir. 11th. Oh shit, that is wrong. No, you're no. Thank you for catching that, yes. That is screwed up, I didn't change that correctly. We meet on, Fridays at 11. Straight across. Yes, thank you, gentlemen.
It didn't say that in Web Advisor. It said we were just Monday, Wednesday.
Ah,
The other
about that.
calculus, yeah, I looked at it yesterday, because I saw your email, it was weird. But the other calculus with Calc 1 class, I think.
Maybe
might
on
evolve.
Thursday.
Well, I saw one that was Monday, Wednesday, Friday. Just
I have a
evolved.
schedule right now. It's the Friday.
Really?
Yeah, usually Fridays, but normally Wednesday.
Yeah, it's a 4-hour class, so we do,
Maybe it just wasn't showing up on my.
yeah, whatever. But you know, you'll be here.
Sometimes, computers.
Computers, what, you can ask your question. Okay, cool. Oh, hi.
I have a question.
Yeah. You want me to pull this down?
Yeah.
Yeah.
The CCI?
Yeah.
Oh, he needs to fix it at one, he put the post-assessment up, he's gonna put the pre-assessment up, he said.
Yes, I will fix that as well.
On world class?
Yes, sir. Yes, absolutely.
See you Friday.
Thank you. See you, yes, see you Friday. Yes. Let's
My
get this
question
shit out of
is,
here. Okay.
what exactly do you get with,
Oh, the H?
Yeah.
Oh, I was just picking it.
Oh, okay, cause I was confused, I was like, where did this?
Sorry, so I'm like, what if H is just 0.1? Then what if it was this?
Okay.
So I was pulling those out of thin air.
Oh, that makes sense, yeah.
Yeah.
Yeah. And then another question
Yeah.
is, the homework is due
Couple, like next Friday or
next
something.
Friday, okay.
Yeah, lots of time.
Okay.
So,
Thank you.
sorry, just real quick, is it okay if I start setting up the computer?
Sure.
It just takes so long for it to log in.
Yeah.
Thank you.
That same phone case, like, way long ago.
Oh, yeah, the mouse. I think they're mouse.
So what is, yeah, what thing. So last class, I wasn't here, I watched you online and I made this. And I was watching your class, I forgot to get here at the beginning of the class.
What?
But this is for you, check it out. I made a bunch of beads. But there's
Oh.
a string with the beads.
Oh, thank you.
I
That's
got me
brilliant,
chance.
thank you. I really appreciate that, that is lovely. Thank you so much.
Alright, well, I'll see you Friday.
Yes, sir.
I just logged in this morning, I saw your email, I don't know if I'm gonna email this because I'm like, oh, use your student ID as the password, but I typed that in and it worked right away, I got it. I'll work, I was gonna work on it this morning, but I was waiting for my law class, so.
For your law class?
For my law class.
Oh, wow.
Lost
You
out.
gonna be a lawyer?
Maybe, but let's see what's going on also. I have a lot of family who are lawyers, and I figure I'd be all right if I went to that.
I have a wife who's a lawyer, so.
What kind of law?
She is a defense attorney, criminal law.
Interesting. I don't know if you stopped your recording.
Oh, thank you. Yeah, let
Um,
me stop that
But,
recording.
yeah, I haven't taken a math class since the junior year of high school. I
Oh.
took Algebra 1, and then I took Geometry